So our Peck lecturer for this year is Jon Bray. Jonathan's been at Cal Berkeley most of his academic career and working in earthquake engineering. He's chair of the GER Committee on Geotechnical Extreme Events and Reconnaissance and the vice president of the Earthquake Engineering Research Institute, and certainly a person that we all know very well. So welcome, Jonathan.
Thank you very much. First, I'd like to thank Geo-Institute for honoring me with this award. It really is amazing. I've had a great career so far. I want to continue to work on it, but it's really an honor to present this lecture on liquefaction effects on structures. And I would like to note that a number of people have contributed to this. A few of them that I really want to mention are Shadeh Dashti, a professor at the University of Colorado, Mishko Chubanovsky at University of Canterbury, Rodolfo Sancio and Jennifer Donahue at GeoCentech, Josh Zupan, who's working with me still at Berkeley, and a number of other people that are listed there as well as others. And the primary sponsor for much of this work is the National Science Foundation. And in fact, much of the things that we've learned from case histories are made possible by a number of people in the audience that are a member of GEAR, the Geotechnical Extreme Events Reconnaissance Association. I had the pleasure of listening to Ralph Peck later in his career, but I got to know him in my introductory soil mechanics and foundation engineering class at West Point. The professors at that time at West Point were all trained at Illinois. And so I felt like I got a secondhand Illinois education. And this brown book is actually kind of the Bible in terms of the foundation engineering or the foundation of my engineering. And so Ralph Peck and his observational method, his take on soil mechanics were a key part in terms of my development. One thing that struck me as an aspiring structural engineer who hadn't quite seen the light to come over to the dark side of geotechnical engineering, the true art of geotechnical engineering, was that people mattered. I loved this book because unlike other books that I had taken and learned from, people were at the top of the chapters. They had plates, and sometimes they were projects, but most often they described a notable figure. And I learned very quickly that if you're going to use somebody's method, you better understand that person, because the personality is intertwined with the method. My students, and just some of them are shown here, have really been blessed at Purdue and then mainly at UC Berkeley with some phenomenal PhD students that have done the work. And in fact, I wouldn't be standing here today if it wasn't for their tremendous efforts. So the outline of my talk is I'm going to describe the problem, and then the Peck Award mentions primarily the work done in Turkey after the Kocaeli earthquake in 1999. So I'm going to go back and reflect on the field observations. I didn't know I was going to do research in this area. It was the earthquake that told me that I needed to do research in this area. And then after the field observations, going in and looking at cyclic testing, looking at some centrifuge testing to get better insight, doing some analysis. Unfortunately, we continue to have to struggle with the challenge of earthquake engineering, and I actually just flew in from New Zealand because I'm spending my sabbatical primarily over there because the centrifuge tests that I was modeling in UC Davis are actually happening at full scale multiple times during the Canterbury earthquake sequence. So I'll talk a little bit about that, and then be bold enough to kind of finish with some recommendations. The problem can be simply stated. All you have to do is estimate liquefaction-induced building movements. What most people do is they apply the techniques that are available. And what's largely available are methods for estimating free field settlement of level ground. Many of these are based on the great laboratory testing of clean sands by Ishihara and Yoshimine in 1992. But what you're really looking at is you're looking at factor of safety against liquefaction triggering. So you can see that on the y-axis of the plot on the right-hand side. And as the factor of safety gets low, you dramatically start increasing your ability to have volumetric strains. And it also depends on the relative density of the soil. And so in this simple case, you could go and calculate the factor of safety of triggering against liquefaction, and you can estimate the relative density. And then each layer would have a strain, a volumetric strain, times it by the thickness of that layer, you sum that up, and you can estimate your settlement. Unfortunately, this is due to post-liquefaction volumetric reconsolidation. So it's good for the free field where that mechanism holds. There's no shear-induced displacements. It does not estimate building movements where the building is imposing shear in the liquefied material. A classic case of this is in the Japan earthquake in 2011, where the building on the left is on piles that are seated below the liquefiable layer. So we're going to use that as our benchmark of it did not move. And then what you see in front of that is that the ground is settled away from that. That entire area in that area has settled about 30 centimeters. That's free field, post-liquefaction, volumetric reconsolidation settlements. That's what those techniques were meant to estimate. What the building owner of the 3-story building on the right cares about is the fact that it has sunk 40 centimeters into that ground, the free field settlement. And so it's actually settled 70 centimeters with respect to the benchmark. It's that 40 centimeters of settlement relative to the free field that has broken utilities or maybe imposed differential settlement or tilt. That's what we want to get after. There have been some great work on this by Professor Tokimatsu, Professor Dobry, and others, looking at case histories and some centrifuge tests with thick deposits. Now, these case histories always had thick deposits of sand. And so they developed this normalization, such as settlement of the building normalized by the liquefied layer thickness. That normalization suggests that it's volumetric strain. If you double the thickness of the liquefiable layer, you double the settlement. That's not true when you have thin layers and you have shear-based movement. I'll show you that later. Now, liquefaction has occurred for many years and centuries. We have the 1906 earthquake, and we have no one forgets their first sand boil. In fact, Ross Boulanger and I were out there on the approach to I-880 and after the Loma Prieta earthquake, and that's my first sand boil that I've ever seen. That's the obvious consequence that we've had liquefaction, is that we have sand boiled, injecta. And part of the controversy is liquefaction triggering, whether you call it cyclic mobility, cyclic softening, cyclic failure, liquefaction, flow liquefaction. And I think that we can jump past some of those controversies if we focus on effects of liquefaction. Because in a sense, there's a material beneath the building that has undergone some kind of transformation, and it has a stress-strain response, and there's a strain deformation field, and then the buildings tip over or a bridge undergoes a lateral spread. In fact, I can show you a lot of details in terms of pore pressure generation and effective stresses and QP plots and things like that. But as a practicing engineer, what you might be worried about, most importantly, is deformation. And so I think it's very important to distinguish flow liquefaction, that's the terminology I'll use today, where you have, because of pore pressure generation, you have the buildup of pore pressures, but you really don't see that in the strains. The strains are slowly increasing, and then boom, you get that large strain potential. That's something that we should be very wary of, and that should be a major concern in terms of stability of slopes as well as buildings. If you take a dense sand, medium dense sand, a silty sand with angular particles, you can generate contractive behavior and get pore pressures, and the effective stress goes down. It can soften, but the minute it starts to soften, it strains and it dilates and it arrests that movement. That's a very different type of soil response, and that's what you see there in terms of cyclic mobility with strain hardening. And so one of the plots, based on case histories by the late Professor Harry Seed, and then adopted by the Yao et al. State-of-the-art paper, is liquefaction triggering, where depending on the seismic demand, the cyclic stress ratio on the left-hand side, the y-axis, and then some kind of penetration resistance, you can say, do I have a demand with a soft enough or soil, loose enough soil where I have liquefaction, or do I have no liquefaction? And so the factor of safety is the resistance over the demand. A factor of safety of 1.2 does not mean the same thing across that space. Because on the left, when I have low blow counts, factor of safety 1.2 says, okay, I've got a capacity that's 20% greater than my demand. Same thing on the right side. But this is a better way of looking at it. This is a plot from Idris and Boulanger 2008 where they're looking at cyclic stress ratio versus penetration resistance, but they're looking at strains, strain potential. And you can see there's a cliff on the bottom part of that figure where you go from 1% to 5% to 50% strain with just a minor variation in the blow count, a minor variation in the cyclic stress ratio. And every engineer is always looking for brittleness and trying to achieve a ductile solution. This is a kind of phenomenon where the earth material is dramatically changing its behavior, and you have tremendous ability, or it has tremendous capacity to basically cause tremendous damage. When you're in the cyclic mobility regime, when you're in the larger blow count range, yes, you can have liquefaction, but it's a more systematic buildup of strain. It's incremental strain. It may eventually lead to strain that's too much in terms of satisfactory performance, but you're unlikely to get the flow liquefaction that leads to the tremendous dramatic problems. Now looking at the Adipazari earthquake, I call this the dynamic version of the Leaning Tower of Pisa, because at the depth of 4.5 meters, all the way down to 9 meters, and below that is some good material as well, is a dense gravel. The water table is at 1.5 meters, so they stopped the foundation, shallow foundation at 1.5 meters. If they had just taken the basement level down to that dense gravel, if they had put drilled piers or piles into that dense gravel, this would not have happened. But remember here is we only had about 2.5 meters of liquefied material to cause that disaster. We saw a number of things. The gear team looking at soils punching in where we didn't look to see that there was much shear. There was just a kind of a volumetric punch down. We did see cases there on the right and the top where you see some heave of the building. That floating foundation in the bottom left became a floating foundation when the heavy walls punched down and the liquefied material squeezed up. And then we have, of course, the V is not for victory, building response. Adipazari means island market. These two rivers were constantly meandering across this area. In fact, a bridge built by the Romans 1,500 years ago is now several kilometers west of the current alignment of the Sacara River. And so this place, even up until 1950s, before they put dams in, had overbank deposits and floods every other year. And so many of the soils in the downtown area are only 50 to maybe 200, 500 years old. What's interesting is to look at the damage statistics, and the bottom southwest part of the city is rock. And so the classic case where the blue colors are less damaged. There are some poorly built buildings in Adipazari, and they did get damaged from shaking, but the normal thing that geotechs are used to. Soil's bad, rock is good. The rock sites didn't have as much damage. What's interesting when you look at the soil is the fact that there were some areas where the buildings that heavily damaged or collapsed, so we're talking significant structural damage, there were areas where almost 50% of the buildings in that district were damaged by liquefaction and ground shaking. And there were other places just adjacent to that where it was only 15 to 30%. And so the idea is just to dig into there and understand why the variation across that area. Part of that is so important to get there after the earthquake and do detailed studies. And so this is part of that gear study. A number of people were involved in that, and Jonathan Stewart and I collected it together in this report. But this is just showing you 60 structures along one line, where building by building, in a consistent way, we collect data on, was there a ground failure? Okay, there wasn't, at 0. Minor ground failure, 1. 3 would be tilt of 3 degrees, settlements more than 25 centimeters, significant ejecta. Same thing with structural damage index. 0 is no damage, 1 is architectural damage, 2 is there's actual cracking of structural members, 3 there's permanent offset of it, and 4 or 5 is partial collapse and collapse. And one of the things you see is you see variation as you walk along this line where there's some significant ground failure and correspondingly significant building damage. There's no ground failure, but there's still some building damage, not as much, but badly built buildings structurally will still have problems even without liquefaction. And then there's more ground failure. That required an extensive study. So the NSF sponsored a study by Les Yat and myself to go out there and investigate. And so back in the summer of 2000, a year later, we performed many cones. We always start with cones because we get a sense of what's there. It's a continuous reading, and so for example, when we're looking at these silts of low plasticity, I can look at the friction ratio, I can look at the tip resistance, and I can say, okay, that's an area where I want to grab a sample. Then we follow on with borings and SPT. At that time, that's 15 years ago, we didn't have the same level of confidence in the CPT as we have now. That ratio is about 3-to-1. Nowadays, I would do 6 cones for every boring, and there have been projects where I've done no borings because there's actually a CPT device that can actually collect samples, and so all you need is a CPT device to be able to do some of the work in terms of liquefaction if you've got sandy or clean soils. In fact, in New Zealand, where it's largely sandy soils, I'm primarily just using the cone. But you can see that the sampling is done deliberately to grab that sample. When I do peer review, one of the first things I do is I look at boring logs, and if I see 2.5 feet, 2.5 feet, 5, 5, 5, 10, 10, 10, I know that the engineer is not thinking. You can always use geophysical techniques, you can use CPT, you can use adjacent properties to look at what's there, and you should have an idea of what's there, what could be important, and then grab samples at the key elevations. If the SPT blow count matters to you, if it doesn't matter to you, don't do it. But if it matters to you, you have to measure the energy. I was very excited about this site because I was told the blow counts were 15 to 25 in Adipazari. That's right on the line. We know when we talk about liquefaction triggering, we want case histories that are right on the line. The ones that are far in or far away don't really matter as much. Well, when we actually measured the energy, first time they did this, we got 80% energy, 30% energy. But when we trained them and said, look at this box, see that number? I want 60 on that number. Then they were trained, and all of a sudden we got blow counts from 4 to 10. So you have to measure energy. The other thing we found is, for example, the short-rod correction that we use in all fields, that worked for softer soils that had lower blow counts, but for the soils in Adipazari, there was no reason to use a short-rod correction when the blow counts were 10 or greater. The other thing you can see is the standard deviation of the measurements. We're doing a very good job of getting that energy measurement around 60%, and that's what we want. So even a trip hammer that's been automated and gets 80% energy, I would maintain that that's wrong. Calibrate it to get 60% energy, because clearly the energy correction ratio is not a linear issue. When we finished this investigation, we could kind of classify soils in Adipazari under 4 different types. Some liquefiable silt on top of potentially liquefiable but slightly older silting materials. We had that silt over dense sand that would not liquefy under the ground shaking that we saw. We had some clay soils on top of liquefiable soils, and then we had some clay soils on top of dense soils that should not have liquefied. Now with that information, we can go back to this mystery, and the mystery is no longer a mystery. We see that our techniques are actually very legitimate. Where there's not liquefaction estimated, there was no observed liquefaction. Where we had liquefaction estimated with our techniques, then we ended up basically seeing the liquefaction. It's critical to take an empirically based method like liquefaction triggering and use case histories to recalibrate to prove the accuracy and understanding. One of the things we saw from Adipazari that was very different from a lot of the other earthquakes is this was not a case of deep sand liquefaction. This was a case of shallow layers of low plasticity silt softening or cyclic failing or liquefying or cyclic mobility issues where buildings basically squished into the material, and we saw material kind of be pushed out, and we saw some heave of the ground, or buildings basically underwent partial bearing capacity failures. A classic case is this tale of 3 buildings that one of the buildings was actually taken down by the time we got there the following summer. The other building, C2, had some significant damage to it, and they were wondering about what to do with it. The owners of building C3 had no problems. These are exactly the same buildings, built by the same contractor, the same structural engineer. Just to add a little bit of spice, the middle building has a black roof. But other than that, they're exactly the same, black tile instead of the tan tile. But major liquefaction, movements of 25 centimeters of settlement, buildings actually slid on liquefied material about 10 to 20 centimeters, And the difference between that is largely that thin, 1 meter thick liquefiable soil right beneath the foundation. You take your volumetric strain calculations and you will not estimate 25 centimeters of settlement with just a meter of soil liquefying. It's clearly squeezing out, and this is more of a shear-based failure. The other thing I said, well, our techniques worked. They worked to a point, because early on we realized that the Chinese criteria, which was recommended in the Yao et al. Paper, which was the state-of-the-art paper at the time, that didn't work. It worked in terms of liquid limit. You know, materials that tended to be the liquefaction, that had eject and had these kind of problems, had low liquid limits, they had high water contents. But the one area that they failed miserably is the percent finer than 5 microns. The criteria says that the kind of materials you have to worry about, also besides having a low liquid limit and high water content, have to have less than 15% of the material less than 5 microns. The actual material that liquefied is shown here has got more than that. And so if you had applied the Chinese criteria rigorously, you'd have said this material would not cyclic soften or fail or liquefy. And really, it brought me back to Casagrande in 1937. I mean, he basically said, be wary of applying grain size to fine-grained materials. In fact, that's the reason for a plasticity chart, to get a sense of mineralogy. It's not the size that matters of the particles, it is the amount of, it's the mineralogy of the particles. If you have an incredibly fine silt made of quartz that just happens to pass through the 5 micron in a hydrometer test, it still acts like a quartz particle. And so we don't need to be doing hydrometer analysis, at least when it comes to liquefaction assessments. We wanted to bring these soils to Berkeley, but we couldn't, not without significant disturbance. A flight from Istanbul to Berkeley I thought would have been too damaging. So we brought Berkeley to Turkey. And so this is a CKC device that was developed by Clarence Chan at Berkeley. You can see it's in Turkey because we have the Ataturk listed, shown there in the picture. And Zetas is the owner of this. They set up the lab. And we did cyclic testing. After Mike Reamer came over and tested it all out, Rodolfo Sanso then was now conducting laboratory tests in Turkey. We started off with one sampling device, and it didn't work that well. And I remember what Dimitris Chrysoftis told me when I practiced at Dames & Moore: you'll never find a better standard sampler than the Dames & Moore hydraulic piston sampler. I bought one of those. I found out Dimitri has one of them in his garage, so I decided, okay, if he's fanatical about it, so will I be. I bought one of those, and I brought that over to Turkey. There are Laval samplers, there's gel pushers, some very, very expensive, elaborate samplers. But in terms of standard samplers, there's not a better sampler for silty soils and clayey soils than the Dames & Moore hydraulic piston sampler. It uses a brass tube. It only shoots 45 centimeters instead of 90 centimeters, so it doesn't get the pile plugging effect. It has a constant inside diameter. It's incredibly thin. The bevel's on the outside. It's got this nice smooth push. It is the best sampler. And then once you take those samples, you basically, like your baby, you basically lock them in the back seat all nice and with the blanket around them. But then you have to check that. Now, NGI has really primarily worked with clays and clay silts, but we're extending this to silty clays and clay silts to look at sample disturbance. We wanted to basically use the barium recompression technique, so bring it back to the in situ stress state. And so if you monitor, and you can always monitor this, the change in void ratio to take the soil back to its in situ stress state and look at that change in void ratio divided by the initial void ratio, you get an index of the quality of the sample. And we did not test these samples unless they were very good to excellent in this range. This is the kind of results we got, and this is really the only plot that has sort of the pore pressures, because I really want to focus on deviator stress versus axial strain or strain development. But we are getting, quote, things that are defined in the Marcuse in 79 that are then cited by Yao et al. 2001 in terms of liquefaction. We are getting pore pressure generation, and we're getting a transient state of softened material. You can see that on the upper left, and then it basically dilates. So we're getting this classic cyclic mobility with limited strain potential. For the very clayey soils, we're getting a more stable response. Now, I thought I'd be able to really look at this and say, okay, PI 0 to 2x one way, and 4 to 8x another way, and 8 to 12. That was actually in my NSF proposal. When I actually did look at these tests, and these are natural soil deposits. They try to be as homogeneous as possible, so we did Atterberg limits in the top, middle, and the bottom of these specimens after the test to confirm that they were somewhat homogeneous, but they're still somewhat heterogeneous. We got these kind of results where there's a tendency that as the PI increases, it's a little bit more resistant. I'm showing you the first cycle in blue, and then the cycle where we got the 3% axial strain, which we defined as failure, in red, and you can see the number of cycles. 11, 13, 15 is about the same for natural soils. It's not until the soils get very high PI in a relative sense that they become much more resistant. Then we brought soil back. Now, obviously, we're bringing soil back to Berkeley. This is the work of Jennifer Donahue with Mike Reamer and myself. And the idea is to go ahead and reconstitute specimens so they are homogeneous. They are all material that have been mixed, so the PI is 10. That's our baseline. That's the dotted line in the background is what we're calling our baseline soil. Soil G that has a plasticity index of 10. And then we took other adiposity silt and mixed it in such a way with the silt and the clay that was there to get materials that had a PI of 2, 5, 11, 7, and 14 in this case. Whether the PI is 10 or 11, you get about the same results. But notice that PI of 5 and 7 are not much different, and very importantly, the PI of 2, that red line is almost on top of the dotted line that's used for the PI of 10. When you get to the higher PIs, you start to get more of that clay-like behavior. So I'm of the firm opinion that there's sand, there's clay, and then there's mixtures. And there's a silty clay mixture, and it's a gray zone. And so I don't think we're ever going to see things as black and white. I think we're going to basically have sands and clays, and then we need to look at this material differently. Here's another case where samples have been made, and in fact, the void ratios are nearly the same, and hence we actually picked them so the liquid limits were similar. So the only thing that varied was PI, hence the water content to liquid limit ratio is about the same. And actually, again, as an engineer, I'd say those are the same line, but if you really want to get picky, the PI 2 line is actually a little bit higher than the PI 10 line. And so again, whether we call this cyclic failure, cyclic softening, liquefaction, cyclic mobility, we do have something where we're losing strength temporarily, and we're losing stiffness temporarily, and then it's dilating to resist that. The phenomenon is very much the same in terms of effects on structures. This is our data from the cyclic test where we had liquefaction observed in terms of pore pressure generation close to 1 and RU equal to 1 near the initial vertical effective stress, or we had 3% single amplitude strain in these triaxial tests. And you can see that, again, making the point, I don't think anyone, in fact, all the people who worked in this field now, I don't think there's anyone that stands behind the Chinese criteria. I think that should be over. And so everyone should be using some other method, Idris and Boulanger, Bray and Sancio, other techniques to basically look at this. I'm obviously partial to Bray and Sancio. I think Rodolfo Sancio is a really smart guy. And so it works on this case history, and it's worked on a number of other materials. And in fact, there's people using it in Canada and other places as a liquefaction susceptibility criteria. And I say liquefaction, again, it's really cyclic mobility. It's a transient state where you get some temporary softening. I also want to talk about I sub C, because this is misused sometimes. I think Peter Robertson, who's in the audience, can talk to you about it in detail. I hope he agrees with me that he picked the names carefully. Sometimes we want to use short names, but I think soil behavior type index, it's an index of types of soil behavior. It is not fines content. It is not a unified soil classification system. It is an index of the type of soil behavior. Unfortunately, a number of our techniques use fines content, or they want the traditional, and there's mapping between those two. Well, it's going to be a bit rough. And I've seen projects where people say, I sub C is 2.59, it'll liquefy. I sub C is 2.61, it will not liquefy. We can all sit back and realize that that doesn't make sense, and you need to really calibrate that on a project-by-project basis. In the upper site, that kind of works pretty well. When you have the low I sub C, you have the low PI materials, the high water content material. We had evidence of liquefaction at that site. But I can show you sites like the bottom site where the I sub C is largely above 2.6, but we still have some significant material that has lower PI than 12, has high water content, and we had a cyclic failure, cyclic mobility kind of response where a building basically settled about 1.5 meters versus 10 centimeters on its other side, so it's significant building tilt due to that phenomenon. So cyclic mobility, susceptibility of fine-grained soils. The percent clay size criteria is unreliable. Do not use the Chinese criteria. Focus on soil mineralogy and sensitivity. I'm partial to checking the PI less than or equal to 12 with a high water content. But very importantly, and others will agree on this, the other problem with the name of liquefaction is liquefaction's bad, and that means if I don't have liquefaction, everything's good. That's not true, because if I have a sensitive clay that will undergo a fabric breakdown, we don't call it in the textbooks liquefaction, but it's a significant loss of strength that can lead to flow slides or tremendous damage to buildings. And so please do not make it a liquefaction or no liquefaction. If the liquefaction doesn't occur, I'm safe. You have to always look at, are there materials that might lose strength from some kind of phenomenon that might be disastrous in terms of the performance of my slope or my building. And then the great thing here is the late Professor Harry Seed, I think, left the laboratory, which he loved in his early days of liquefaction testing, to go to the field because he had to. He couldn't get clean sand deposits that were loose into the laboratory and test them effectively. We have freezing technologies and things like that where we can do that, but they tend to be more expensive. So we stick with CPT and SPT. But these soils can be sampled effectively. They're silts with a little bit of clay. They have PIs of 4 and 7 and 10. We can sample these, and there's no excuse to not bring them in the lab after they've been sampled effectively and test them. And when you go back to the classic work of late Professor Harry Seed in '79, where he did all that testing on clean sands. We've gone back with Donahue's work and looked at the effects of void ratio, stress history, and those same kinds of things matter. So when you take sampling, which will never be perfect, you always have to think about, how have I changed the stress history, or how about time under confinement? In fact, stress history and time under confinement before testing are more critical for slightly plastic silt materials than they are for clean sands. So Adipazari was a great lesson in terms of understanding liquefaction and its effects on structures, but we were really tied in terms of these case histories, or restricted, because we had one component of one ground motion recorded for that event. I mean, there's really not much more important than the input ground motion, and we had just one component. And it was 3 to 4 kilometers away from the heart of the city where we were doing most of our work. So if nature's not going to provide us, we haven't been smart enough to put pore pressure sensors in the soil beneath the buildings and done all the instrumentation of the case histories before the earthquake hits, we can make little earthquakes up at UC Davis on the centrifuge. And so we can start looking at the effects of thin layers. And so one of the things that's unique to this testing is we used relatively thin layers of liquefied material. We started off with 6 meter thickness. I'll do everything in prototype scale because that's how engineers think. You divide these by 55 and you get what we actually had as dimensions in the centrifuge, and we spun it up to 55 Gs. But we had 6 meters initially because that was the thicker layer that we could kind of see how our results responded or compared with others. But then we went to 3 meters with the idea of, can 3 meters of liquefied material have about the same consequences in terms of deformations? Let me show you this video real quickly. And we focused, there's always a struggle on instrumentation. You know, what should you have? But we decided to focus on displacement. So we had displacement LVDTs at each corner. And that's what, one of the first things that I had been taught, my concept was liquefaction is an undrained phenomenon. And it's undrained, everything is constant volume, and then we get post-liquefaction, reconsolidation, and we get drainage. That's not what we saw in the centrifuge. And I'm a little worried about this because centrifuge sometimes it doesn't capture all the mechanisms, but then we went back and looked at the interviews of people in Turkey, and they talked about when they exited the building, much of the settlement had already happened. And so settlement's occurring during strong shaking. It's not undrained, drained, it's response with some drainage occurring during strong shaking. The other thing is it's I hate to do this, it's on a Monday morning, but it's a little shakedown. It's a little disco thing, okay? It's ratcheting down. And the more mass you have, I've been exercising while I'm in New Zealand, so I'm a little bit lighter than I was after the holidays. The more mass you have, the more inertia you're going to basically work yourself into that soil. So it's clearly an SSI problem. This is the 3-meter thickness. We looked at both 50% relative density and 30% relative density. I don't want to get into all the details. The time history shown on the bottom, the pore pressure generation shown on the next plot up. You can see that we got an RU of 1.0 for the 30% relative density material. Very importantly, you don't have to get full pore pressure generation. We didn't get that for the 50% relative density material, but you still get enough softening to where we got about the same amount of settlement. We tended to get less settlement at 50% relative density soils than 30%, but the most important thing is look at the significant amount of settlement that's occurring during strong shaking. Then after strong shaking, you've got this pore pressures exiting, the high pressure, water pressure, the stress being retransferred to the soil skeleton. Now you're getting the familiar shape of a consolidation curve. If you're looking at it at arithmetic time, if I change it to log time, it would look more familiar to you. And the settlement of the building is significantly more than the free field. So like we saw in Japan, the buildings are settling into the free field. The free field's settling, but it's the buildings in the free field. Another important thing is looking at water pressure under the building and away in the free field. Because of the building and the extra stress, you have a higher capacity to develop higher excess pore pressures under the building. And so you have hydraulic head going from underneath the building away. And so the minute water's leaving, because Darcy's law acts, as soon as you have these high hydraulic gradients, water's leaving from underneath the soil, that means the sand can settle down a little bit. So you are getting some volumetric strain locally as water is moving during the earthquake. So this leads us to mechanism. And one of the most valuable things about centrifuge testing is you control. I know what the time histories are. I measure the time histories. I know the thickness of the layer. I know the relative density. But you can look at mechanisms. You can really focus on mechanisms. I like to break things down into volumetric and shear. So volumetric, there's a number of mechanisms, but I listed the 3 most important. We are getting partial drainage. Water is moving. When you have a high transient hydraulic head, water responds to that. And so you have water moving from underneath the building, and that leads to local volumetric strains. If you get a high RU, if you get a high excess pore pressure, so the excess pore pressure divided by the initial vertical effective stress, if you get a high RU and you get liquefaction, you get a destructuring of the soil and it resediments, that leads to a lot of deformation. If you don't have that, then obviously you don't get that phenomenon. That's obviously something that we don't model well with our constitutional models. And then we have the post-liquefaction reconsolidation. During the earthquake, the water's being generated probably faster than it can dissipate. Eventually you get to a point where the strong shaking starts to subside and you start to get water leaving at a higher rate than is being generated. So you are getting transfer of water and then the stress being transferred to the soil skeleton, and you are getting that. But as you saw in those time plots, that's a much smaller part of the total settlement of the building. Most of the settlement's occurring during strong shaking, when that's not as important. The shear-induced deformations. If you could base isolate a building from rocking and shaking, if the soil generates pore pressure and it softens, then it's less stiff. And so if you had put a CPT in right in the middle of that earthquake and used the Schmertman method, you would have basically said, oh, that building's going to settle 20, 30 centimeters. And so that kind of phenomenon is basically a partial bearing failure. And of course, if it exceeds, the driving stress exceeds the residual strength, you can get these bearing capacity failures. But then probably the most insidious mechanism is SSI-induced ratcheting. Because the building's pulling up on the soil, soils don't like tension, and then right before it pulls up and disturbs it the most, it comes back and hits it with a hammer. And it works itself down into the soil. On the BART system, which I was a peer reviewer of, Fugro did a lot of phenomenal analysis and some centrifuge tests with Bruce Cutter at Davis. The tunnel was lighter, so it actually ratcheted itself up. And so it's not a instantaneous deformation. It's basically a ratcheting of the building working itself in to the softened material as it undergoes these transient states of low stiffness, low strength. And then something that I did not see in the centrifuge, and I did not see in a lot of case histories before New Zealand, is I can't forget the obvious. Ground loss due to ejecta. If you've got a half a meter of sand on the surface of the earth after an earthquake, that came from somewhere. And if that half a meter of sand came from underneath and came up to the surface, you now, or the surface is half a meter down, and if that sand came from underneath your foundation, you've mined out soil underneath your foundation. That has obviously disastrous effects. And so, again, I haven't quite developed a constitutive model to handle that yet. Going back to this plot, which I told you that I've used this in practice, but I'm not using it anymore because it's normalized by the thickness of the liquefied layer. And that would say it's all volumetric strain, and it's not. And so I did our first test with a thickness of 6 meters. This is a test done by Sinead Ashby as part of her thesis. And that coincided with tests that Elizabeth Hauser had done with Nick Sitar, some work by Ricardo Dobry where they had a thicker layer of liquefiable material. It matches the case histories. But just because the normalization works for a certain set doesn't mean it's fundamental. We have to be wary of normalizations that are not fundamental. And if it's not volumetric strain that's controlling, it shouldn't be the thickness of the liquefied layer. And when we went to the 3 meter thickness, all of a sudden the normalization doesn't work anymore. So the key thing here is I just need some soil beneath my foundation to liquefy. It can squirt out or you can shear laterally and I can get significant movement. And there's no way a volumetric mechanism procedure is going to capture that. The other thing I noticed when we looked at the black lines, which are the settlement, they looked a lot like something I'd seen in terms of ground motions. There's something called an Arius intensity plot, which you call the Hused plot, but Arius intensity is the integration of the acceleration squared. You can go back to Arius' paper in 1970 or go to Kramer's textbook and see that, but it's essentially telling you that the energy that's being delivered to the soil. And what you see here is when you have a rapid rate of energy being introduced to the soil, you have a rapid rate of building settlement. In the TCU motion, which we deliberately chose because it has a slower rate of movement, you can see that the building is basically settling at a slower rate. And so this gave me a great opportunity to thank those professors that introduced me to Ralph Peck back at West Point. And so I came up with, yes, sir. Sir, what you need is another intensity rate, is shaking intensity rate. It's essentially the amount of energy that's being put into the soil during significant ground shaking, which is the duration from 5 to 75 on the Arius intensity plot. When you have a high rate of shaking intensity, you get a high rate of building settlement. And so I think cyclic stress ratio and magnitude doesn't quite fit in terms of, or capture some of the things that we're looking at here. With the fourth centrifuge, it was actually Sinead's idea to say, let's not do what you wanted to do and what you wrote in the proposal. I've learned something. Hopefully you've learned something. Let's challenge ourselves and let's really see if these mechanisms that we've identified from the first 3 tests are what we think they are in terms of their relative importance. So, and it will also give us a sense in terms of a positive aspect is how to mitigate these measures. And so we used 3 identical buildings. They're shown on the right-hand side there. The middle was a baseline case, nothing different than what we had done. But on the upper left, you see a structural wall. That structural wall is not tied to the building. It's just around the soil. There's a little bit of a gap. So the idea is we're not turning this into a deep foundation, but we are putting a wall. That's not allowing water to go from underneath the building to outside, and it's not allowing shear-induced deformation. As an alternative is the water barrier. It's a flexible membrane that won't allow water to go from underneath the building to outside, but it's flexible, so it will allow the shear-induced deformation. So let's see if our concepts hold water as well as the wall does. The blue line is the baseline case. That's shown in the upper right-hand corner, and there was shear deformation, there was volumetric deformation, and we got about 110 millimeters of settlement for this moderate Port Island shake. The water barrier is taking one of the mechanisms out. It's taking out that local water, the water that's higher pressure under the building trying to go out laterally, and so the settlement's reduced by about 1/4. The structural wall is taking out even more settlement, and in fact, I think it's more than it would have been. If you look carefully in the right-hand corner, the right bottom corner, you can see that the sand's pushed up a little bit. Our little plug, because we want to make sure that the building wasn't touching the structural wall, actually the water pressures were so high and they couldn't escape, they found a way of escaping, and they shot up along the side of our foundation. So part of that settlement is because of the release of the water. But even with that, by not allowing the water to move until that plug failed and not allowing the shear-induced deformation, we got about half the settlement. So I think these mechanisms are a good way of thinking about how pore pressures develop, how they move, how the soil can shear in response to an earthquake. Working with Peter Byrne, Sinead Ashley and I did some flak analysis. And again, we picked the UBC sand model because it's well calibrated for looking at shear-based deformations. In fact, it was developed to look at dams. This is a case where we're looking at shear-based deformation under a building, but it does a very good job of doing a lot of things in terms of pore pressure generation and such. But I'm showing you its capability to capture the strain, because in the end, it's the deformation that's leading to the settlement. And so the nice thing about a constitutive model, if it's calibrated, is you can look at details. Like, in this case, the shear strain was a significant deformation of this building as it underwent partial bearing failure and SSI ratcheting. There was some volumetric strain underneath the building with the water moving out, but it was a smaller part of the entire picture. And so shear-based deformations are key. And so in terms of mitigating this, some kind of ground improvement would be focusing on the shear-based mechanism, but also you want to look at maybe partial drainage as well. Just showing you one of the results. The truth is the centrifuge measurements on the left-hand side, the flak simulation with the UBC sand models on the right, just a general sense of the pore pressures, that we get the general trends about right in terms of the bottom, middle, and the top of the liquefied layer. Most importantly, we're getting the settlement to occur during strong shaking, and we're getting an estimate that's somewhat reasonable. We're estimating about 150 millimeters of settlement, and reality is 110. We're not going to do much better than that in this field. It's a very difficult field. In fact, when we look at all of our analysis, with a calibrated model that's well understood, that it has its limitations, when we calculate large settlements, we tend to get large settlements. That's a classic thing that we have. We see this in Yout et al. 2002, lateral spreading. We do a pretty good job of estimating settlements when we get a lot. If it's a big earthquake, massive liquefaction, our models work well. But we typically don't care whether a building settles 50 centimeters or 80 centimeters. That's too much. And so where we need to work in performance-based engineering is on the bottom part of that plot. And that's a bit humbling, because liquefaction's a brittle phenomenon. Where we didn't do a good job, we predicted it'd be 100 to 150 millimeters of settlement, and there was only about 50 or 20 millimeters of settlement, is because we're outside of these error bounds, is because we said the pore pressure was going to get up to maybe 0.7. We're going to get softening, and we get liquefaction, and we get movements. The actual test, maybe because of the drainage we didn't get hydraulic conductivity right, the actual test, the actual material pore pressure generation was a little bit less. It didn't quite soften that much, and so it didn't settle as much. And so we have to be wary that liquefaction is something that we have to do a sensitivity analysis on. So the findings from this part is building settlements are not proportional to the thickness of the liquefiable layer. Free field settlements, yes, go ahead and use your volumetric strain procedures, but building movements are largely a result of shear strains and volumetric localized strains, and of course, very importantly, as I'll show you soon, is the loss of ground with ejecta. Building settlements related to the shaking intensity rate and the relative density of the soil. These observations, this is important, they're not captured by available techniques. Last is the Canterbury earthquake. Something that I had not done in previous studies is actually measure the amount of sand that came out of the ground. We noted that there was sand, or a lot of sand, but I think that was a mistake to not measure the amount of sand and actually do this precise calculation. So the next time there's a major earthquake, we're going to measure ejecta when we have these kind of case histories. I mean, that bottom left-hand picture looks like a snowstorm in Buffalo. I was up in Buffalo one time, and that's what it looked like if I just replaced that sand with snow. I mean, it was just amazing. There were places where there was 0.5 meter to 1 meter of sand ejected out of the ground, with disastrous consequences to the houses. What's remarkable about this is while I was doing something odd in terms of a centrifuge test takes a lot to do, and so we go ahead and set that up, and we shake it a little bit, we shake it a little bit more, and we shake it a little bit more. I mean, how many times are you going to have 3 or 4 earthquakes hit the same site? This place has been hit by 7 earthquakes greater than magnitude 5.5, dozens of others. Some sites have liquefied 5 times. Some sites have never liquefied. Some have liquefied 1 time, 2 times. This is a full-scale shaking table test as the city of Christchurch, unfortunately, responds to multiple earthquakes. This is mapping by Trubanowski, where the red zone is the moderate to severe. Yellow is low to moderate. You can see major parts of the city liquefied under a magnitude 6.2, only a 6.2, but it was close. So the distance was short, so the intensity was high. The further away, it was only 30 kilometers away, magnitude 7.1 led to less liquefaction. I'm just showing you the severe liquefaction zones in white. And then I picked up on the June earthquake. They've had others. They had another 6.0 in December 2011. It has a smaller patch. And so this is really going to challenge our liquefaction evaluation techniques because we have a full-scale case histories where we look at the same sites undergo multiple levels of ground shaking. Everything's very well recorded with dozens of strong motion sites. We have actually 8,000 cones have been put in the ground. 8,000 cones, incredible database. Just focusing on the central business district, which is about a 1.5 by 2 kilometer rectangle in the middle of the city, right to the right of Hagley Park, the green zone that you see. There's 4 strong motion stations that are around that area. And of course, there's ones further out. So I'll focus in on those and just look at 5 of the important earthquakes. The Darfield earthquake started off the 7.1, but it was further away. Then we had a 4.8 that was close, that there wasn't significant damage. 6.2 was the big one in terms of the CBD. Darfield was hit, the outside areas pretty hard. And then 2 other magnitudes, 5.9s and 6s. This shows the recorded ground motions in terms of the median PGA of the 2 components. I used the magnitude scaling factor from Idris and Boulanger, and I just estimated what the cyclic stress ratio would be right below the water table for shallow liquefaction. So we can kind of assume that the ratio of the total vertical stress to the vertical effective stress is around 1, and R sub D is around 1. And so you get that equation on the bottom. The important thing here is look at the fine-tooth cone here. Is 0.07, and there was no liquefaction observed in the CBD. When you get up to 0.09 to 0.1, we saw low levels of liquefaction in isolated locations in the CBD, the Central Business District. And when it got up to 0.2, we saw severe liquefaction. So this is going to challenge our fine-tooth comb in terms of really testing our evaluation techniques as we try to perfect, we'll never do it, but we try to perfect our performance-based earthquake engineering. We saw the similar things. We saw buildings sliding, tilting, settlement. We saw individual spread footings. Unlike Turkey, which had these massive foundations, so they moved as a rigid block, these had kind of foundations that we use more in the US. We had individual spread footings that were put together with tie beams. And so we measured angular distortion very precisely, and we saw cracking in the beam, which you can see clearly, which we should get at an angular distortion of 1/70. We saw buildings where the ground settled away from pile-supported structures. And then we also saw something where we saw massive liquefaction but no settlement of the building because everything kind of moved down together because they were supported on gravel layers that were floating. Through the downtown area, we see the liquefaction through the CBD. And I want to focus on a site, just one site, that's right in this area. Another interesting thing about Christchurch is it was just settled recently. Littleton was Christchurch in 1850, and they realized it was too small, so they went over the mountains, and like a good city, they decided to go ahead and build on the swamp. Now, they were smart enough to put the cathedral on a shallow gravel, and so the cathedral actually had no liquefaction issues. Unfortunately, it was a brittle masonry building, so it had significant structural damage, but they were smart enough to actually avoid the liquefaction there. But when you look at this map, you see that the Avon River, where it's channelized now, wasn't there all the time. In fact, this is a lot like Adapazari, a lot like Mississippi, a lot of these soils are overbank deposits, and they've just been deposited in the last 50 to 1,000 years. And so they're relatively young type of soils. A lot of them are 100 to 500 years old in the upper couple meters. And if I focus in on this one area, you can see it's kind of got a zone where there was a buried stream in that area. And sure enough, the buried stream actually cuts the left side of that building, as shown in this picture. With a level, laser level, we measured the deformation, and we saw that the building, the north side of the building, which is on the right, went down 6 centimeters relative to the short building next to it that appeared to go down with the ground. So the ground and that building to the right probably went down a little bit because things liquefied in the area a little bit. But it was, that building went down 6 centimeters with respect to it. And as you went further out, you got closer to that buried stream channel that clipped the corner of the building. And over the last 2 bays, most of the settlement occurred, about 20 centimeters of settlement over the last 2 bays. That angle distortion is about 1 over 1 over 50. And so the kinds of cracks that we saw in the beams are to be expected. A very important thing is look at the ejecta. That ejecta probably came out from underneath that shallow foundation that's supporting that column. So it's not a surprise that that column moved down significantly. We've done CPTs in this area as well as some borings to calibrate it. And I'm showing in red the shallow liquefiable soils as calculated by Robertson and Ride, but I get the same answer when I use Idris and Boulanger or Moss Seed et al. They all say that that's going to liquefy. And then we have deeper liquefaction, which is shown in yellow. So across this area, we had liquefaction, and these are sandy soils, so isopsy is really not an issue here, that basically led to some overall settlement. That's probably that free field settlement. But what the building cares about is the shallow liquefaction. In this case, it's only on one side of the building, and so that's why we had that significant differential settlement of 25 centimeters across the building. What would we do? What kind of insights would we gain if we used the traditional approach of post-liquefaction reconsolidation settlements, which were meant only for the free field? Well, we capture that we get about 10 centimeters of settlement here, mainly because of the deep liquefaction. And we capture some deep liquefaction and that shallow liquefaction here, and we say 15 centimeters. There are engineers that take CPT locations, and they do these calculations, and they use that to estimate differential settlement. They should not be doing that, because the actual settlement was 15 centimeters in that location and 40 centimeters relative to our benchmark. It can't possibly work because it only focuses on post-liquefaction volumetric strain. It's not looking at shear. It's not looking at the effects of ejecta. Now you say, well, what can we do? You know, I come here and tell you what not to do. I'm like your father or your mother. First is liquefaction severely damaged the ground and the buried utilities. In fact, you got to think about it as an infrastructure. Tom O'Rourke's working on the buried utilities. The heart of the city is literally broken. 70% of the buildings in the central business district have been demolished or soon will be demolished. 70%. Each earthquake was well recorded, so there's an opportunity to look at things like magnitude scaling factor and other aspects in terms of performance-based engineering. And like Adipazari, like I see a lot of cases, it's the soil right beneath your feet that matters most. That loose, shallow, silty sand, when present, led to most of the damage that I have observed in the central business district for the larger buildings. I'm studying a building that we still have to get access to, but I've got the observations. We just have to add some CPTs. A 25-story building that was taken down. It had some structural damage, but it was repairable, but the entire building tilted about 1/2 degree on a big mat. And so it's not just 8-story buildings. It can be 12-story buildings. It can be 20-story buildings on a big mat. So recommendations, 2 slides. 1, there's no reason not to perform cyclic testing if you've taken the care, and you should, in terms of sampling effectively, to get undisturbed samples. And then you check that by using something like the NGI criteria. And see what the response is. And call it whatever you want to call it, but say, this is how the stresses and strains develop in the laboratory. This is the way the strains develop. Let's calibrate my numerical model against that. Let's calibrate my insights against that. And let's see how that system responds to that kind of behavior, whatever I call it. Because that's what it's an engineered material response to earthquake shaking. If you are going to use triggering techniques, realize that they were developed for sands and non-plastic sands. When I looked at the 1985 Seed et al. Database, he only had 13 case histories where he had more than 35% fines. And those case histories largely were non-plastic fines. So why would a method that was developed for sands and non-plastic silts work for silty clays if it's an empirically based method? So you have to use your judgment. And so I'm saying, you know, a technique like Bray and Sancio, where you're looking at PI, plasticity index, and water content, can be applied conservatively, but really there's no reason not to take samples and test it. In terms of the case where you have buildings on level ground with no free face, this fits into this conference. We're talking no slope, okay? If you have a slope, then lateral spreading is a big issue, and slope stability is a big issue. Whenever you get large lateral movements, you get big vertical movements, and that's a special case. And in fact, you have to mitigate that issue. But you do often have cases where you're away from the riverbanks and you have level ground. In those cases, if you have a pile foundation, very importantly, the neutral plane has to be below the liquefiable layer. So bored piles did not do well because they take friction through skin friction, and when the ground liquefies, then they transfer that load down to the base, and you get settlement. You want to drive those piles into the ground. You not only get densification from the liquefied soil, but you are developing the neutral plane in the bearing layer. The soil, the pile, the ground's already moved down that pile, and so if it liquefies and moves down a bit, you're not going to get significant additional settlement. And that's what we see in the case histories. Shallow foundations with deep liquefiable sands, you're out of the stress bulb, then everything kind of goes down together, and it is largely post-liquefaction volumetric strains. So you can say how the entire city and your building is going to go down. But if you have a shallow foundation and you have shallow soils that could liquefy, you're putting some significant shear in there. If you're in the seat of settlement, you're going to get large shear-induced movements. You cannot use 1D techniques that are based on volumetric strain only to calculate that. So you should do effective stress analysis. That's been calibrated with good earthquake and soil characterization. And if you're not going to do effective stress nonlinear analysis, it's better to use engineering judgment, in my view, and kind of look at case histories and make an estimate than to use a technique that is clearly not appropriate. Thank you.